In this video, we're going to take a look at vectors in the plane. And vectors in the plane just means that we're considering two-dimensional vectors only, right? So the plane would look something like this, like the typical XY plane that we deal with, right? So that's X over here. Sorry, the tablet's giving some trouble, but X and Y. And then let's say we have a vector like this, right? And we'll call this vector V. I'll explain what all this means, but this is what we're considering. We're not yet considering three-dimensional vectors. Okay, so this is where we're starting. Now, what is a vector? Well, a vector is similar to, in some ways, a scalar. And usually when you hear about a vector, you'll also hear about scalars. So I'll introduce them together. A scalar, so it's spelled like this. Bro, sorry, this is kind of bad. SCALAR, and then obviously vector is just like this. Both of them have one thing in common. Both of them have a magnitude, right? And a magnitude is just like a length. So, or a length or any quantity with units, right? So if I'm talking about distance, for example, it could be 3 feet, 2 miles, something like that. And so both of them have a magnitude, but a scalar is just the magnitude. And a vector also has a direction, right? And now initially over here, we might talk about direction in terms of slope. We might talk about it in right, left, northwest, south, east, that sort of stuff. But you can also give it a more mathematical definition of direction. And we'll kind of discuss that later on over here. But that's the main fundamental difference between vectors and scalars. A vector also has the component of a direction, right? Now we've drawn a vector over here, and we actually, this vector and this vector are the exact same thing. And the reason is that a vector, the only thing that really matters in a vector is that a vector is free to move about however you'd like. And the point where it starts is usually called the initial point, the starting point, and then where it ends, which will be over here, is the terminal point. You draw it as an arrow going in that direction. So this vector is the same as this because you basically just moved it over like this, right? You've translated it to the right a little bit in the positive along the positive x-axis. But these vectors are the same, and we'll go into why we know they're the same later on and how you can actually check that as well. But a key idea is if you have this vector, and now I'll do it in a different color, same exact shape, same exact location, but you flip the direction, right? So now it's going the other way. This is no longer the same vector. It's actually the negative of the vector. And we'll talk about all of that in detail. But that's kind of how, that's one way to represent a vector. Now, what if you want to represent it a little better? Well, you can just take the initial point to be 0, 0, and then label the end point as a pair. So something like this, right? Like x, y. This will give you some vector v. Okay, now over here, notice this little arrow on top. You put this to denote something being a vector. In a textbook, you might see like an extra thick, like bolded V, like this. This is a vector. U, like this, right? But it's harder for me to do that here, so I'll just put these instead. They indicate the exact same thing, same exact meaning. Anyway, so that's what vectors and scalars are. Now let's think about it, right? So what did I say over here? We're taking the vector V as starting and starting at the origin. So its initial point is the origin, and then x comma y give you the coordinates of the endpoint. So again, x and y over here. We'll start right over here, and then let's say it's like 5 and 6, so that would be right around there. So this is our vector v. Now what if we had another vector, right? And it's got an initial point of 1 comma 4, and so this is, you would write it like this. It's got 5 units in the x direction, and it's got 6 it's up 6 units in the y direction. We use these angled brackets and not regular brackets because that's with the point, right? Over here you're using square brackets. Again, that just goes hand in hand with the vector notation here. No, so if we have 1 and 4, and then we have 6 and 10 as the endpoint, so this is initial and this is terminal. This is actually the exact same vector. We're just starting elsewhere. So we're starting like over here, and then exact same shape, and it's over here. So it's just like a translation. How do we know that they're the same thing? Well, this is where we come to like the first kind of analytical piece of math over here, right? To find the vector, the coordinates of the vector, we just do the terminal point minus the initial point, right? And that makes sense. We're talking about the change in x and the change in y. Over here, this will just be 6 minus 1, 10 minus 4, in that order, right? Because we're doing terminal minus initial. And this is just 5 and 6, which is the exact same thing. Now, that makes sense, right? It's the same vector, it's just at a different position. There's some more properties of a vector, some of them that are very important. So let's kind of dive into those now. But before that, actually, I mean, there are different ways you can go about doing this. Let's talk about those first. So the magnitude of a vector, like like I mentioned earlier, magnitude is just like a length, like 5 feet, something like that. But over here, when we got 5 feet in one direction, 6 feet in one direction, how do we give just one magnitude, right? Because there's a 5 and a 6. Well, it's the distance theorem, the Pythagorean theorem, right? It's very easy with 2 dimensions because it's just what you learned probably earlier on in like algebra one. Um, just the Pythagorean theorem. So the magnitude, which you denote like this, you put lines around the vector. This is now going to be a scalar quantity. Why? Because we're just getting a magnitude. There is no direction involved. This is going to be 5 squared plus 6 squared. And what is that? That's 25 plus 36. So that is the square root of 61, I believe. Is that? No, wait. Yeah, 61. Square root of 61. And again, this is not a vector, right? So this is a scalar because it's just the magnitude. Okay. Um, so that's one thing. Now, what about the direction? How do we know the direction? Well, like I said earlier, there's right, there's left. Over here, if you just give this is enough. It gives you the slope, right? So the direction is like, it's like a slope of 6/5. But there are other ways to just explicitly find the direction as well. And one way to do that is by working with unit vectors. So what's a unit vector? Well, the vector part is obviously a vector. The unit part of that indicates that the magnitude of the vector is 1. So let's do a little experiment here. So we have v over here, and let's say, actually, let's talk about two very common unit vectors, and you've seen them. Just in this video, you've seen them already. So we have x over here, right, on a regular like Cartesian plane, x and y. The vector 0, 1, sorry, 1, 0, right here. Um, this is called the I unit vector. This is the I direction, and then this is the j direction. So this over here, 0, 1, that's an angle bracket. And you denote them like this. It's like I hat, j hat. I'll call them I hat, j hat over here. And then in 3 dimensions, there's also the k. There's also k hat, which is in the z direction, positive z direction. So that would look something like this. And then of course you'd add another 0 here, right? But we don't need to worry about that because sorry about the weird handwriting, by the way. Anyway, point is over here we're just talking about planar stuff, so we don't need to worry about the z direction. So these are the two unit vectors, and we can express. So if we go back up over here, right, we have the vector v equals 5 and 6, right? 5 in the x direction or the I direction, 6 in the other one. So we can also write v just like this: 5 times the I vector plus 6 times the j vector, right? And one way to think about that is we're going 5 times in this direction here, and then 1, 2, 3, 4, 5, 6, 6 times over here, same exact thing, right? So that's how it works. Now, we can express the direction in terms of I and j, right? But over here, like it's still not clear because it's getting kind of muddled by this. So to get just the direction, what we do is normalize a vector by dividing it by its magnitude. And what this does is it gives us a vector of magnitude 1 in the exact direction that you want. And that's usually how you define direction when you're working with vectors. You can also use angles in that, but it's not going to be a nice, convenient angle here. This angle theta, just from like basic trigonometry, would be the like arctan of 1.2, 6/5, right? But we don't want to work with that, so we'll just write it like this instead. It's 5i. And now over here, it's kind of a leap of faith, especially if you've never seen vectors before, that we can do this because we're kind of dividing a vector quantity by a scalar. Like, how does that work? We'll get into that like very, very briefly in a few minutes. But this is basically the direction. And one way we could denote this is like this: v hat, right? That's kind of ugly, so just v hat will suffice. But this is the normalized vector, right? This is called normalizing the vector because you're giving it a standard magnitude of just 1. You can also call the magnitude norm. By the way, there are a lot of different terms that come up. So magnitude, I think some people call it modulus. That's more with complex numbers, I think, but that also works. Norm, length of a vector, size. I mean, size is more informal. I don't think you come across that, but length, all of these things definitely, they're all the same thing, right? The absolute value as well, I guess. But that's it. So now let's talk about some basic operations, right? And I already showed you some of them. If you've got a vector v and you've got a vector u. The sum of these is just, well, you just add the components, right? You just add components. So let's say it's, again, we're just dealing with two dimensions. So let's say we had Vx and Vy, like V sub y, V sub x. These are scalar quantities inside, right? These are like the the dimensions, not the dimensions, sorry, the position of the vector. It's just defining the vector, right? So notice how over here 5 and 6, not here, over here 5 and 6 are scalars. They should not be vectors. So V sub x, V sub y are not vectors, as scalars. And then same thing here with u. Sorry, it looks really messy, but u, y. This will just be u sub x plus v sub x. I switch up the order, I know. For u, I just put dots on top so that you can like make out clearly. Sorry, no. Yeah, see, it's like really messy, so I'm not really doing it well. And then u sub y plus v sub y, right? So that's how you do it, like this. When you're dealing with negatives, or actually just in general, when you're dealing with scalar multiples, like this would be c times v sub x, v sub y, and this would just be c times v sub x, and then c times v sub y. And you can combine these two rules, and then you'll see that c times the vector v plus the vector u, when you look at its components, it's going to be c times the component of vector v plus the component of vector u for each of the components. So it should be x and y over here. It sounds like a lot, but it's like very, very straightforward. Let me give you an example. If we're adding a very simple example, let's say we're adding this is of course the I vector, and then this is the j vector, right? The j hat. When we do this, we get I plus j is equal to, we just add the x components and the y components, and we get 1, 1, right? What if we did 3i plus 2j? What would this give us? Try this yourself. It's not too difficult, same exact thing, right? Now we're combining both the rules from above, but this is what we'll get. That's one of the main rules. Besides that, there isn't much more. Oh yeah, so now let's say you've got just a vector v like this, right? And you can think about it as being like, maybe let's say 6 and or not 6, let's do 7 and 3. These are the components of the vector. Sorry, 7 and 3, it's like very laggy. 7 and 3. And let's call this like the vector v. What would negative v be? This would just be, well, it's negative 1 times 7 and 3, right? So this would just be negative 7, negative 3. And this, when you look at it, it'll just be the opposite of the vector, right? Like it's just like same exact vector flipped, rotated 180 degrees. You could think of it like that as well. So I think that covers it for the main properties of vectors and just what vectors are. Now, I know a lot of this is kind of maybe abstract, especially seeing all these formulas. Might have been a little tricky, but it's really very simple. It's very similar. It's just an extension of what all you've learned. The key takeaways from here, just kind of going through it all again. The main difference between a vector and a scalar is that a vector also has a direction. When you're considering a direction, there are a lot of different ways of representing it. Of course, you can like draw it out and see. You can give the angle, right? Like this angle over here, bring it to the origin, and then that angle here, theta, you can use that to define it. You can give the slope, right? That's kind of what we did over here. But one way to do it is also by using a unit vector, right? By standardizing the vector, normalizing the vector, and then taking that unit vector v hat, for example, and that will also give you the direction. The magnitude is just by the Pythagorean theorem, and you'll see that this logic extends to infinitely many directions. It's always the same way. It's the square root of each of the components square, the sum of the squares of each of the components. And then yeah, these are some properties over here. You can prove them, I guess, if you want, but like it's not really, hopefully it shouldn't be too big a leap of faith for you to take here, right? You add vectors, you add the components, scalar multiple, you multiply by the components, right? So it's very hopefully for you very simple to think about. There's really not much practice I can do here or like give over here because it's pretty simple, but you'll build upon these ideas in future sections like 11.2, 11.3, and hopefully you'll have a better appreciation for them there. But I'm almost out of time in this video. Thank you for watching. Hope you enjoyed. Hope you learned something new.